So our next speaker is Ted Bergin, and he's going to pick up this theme of volatility and focus specifically on water, from cores and clouds to disks and planets.
Okay, so thanks to Colette for setting the stage here. And so I have a story to tell, and this story has some gaps. But before I do so, we have to acknowledge our excellent team here, Avina van de Schaak, Jonathan Lean, Derek List, and myself. And also, I'll be showing you a lot of data from Spitzer and Herschel, amongst other things, and so we have to be grateful to ESA and NASA for doing this for us. So, all right, this is the story of this conference, right? We start out here, molecular cloud, prestellar core, protostar, megadisk, and then the planets, right? So this is huge spatial scales, densities going way up, temperature going up, down, doing all kinds of things, right? And that can affect the formation of water and, of course, its excitation, so how we can track it, how it gets planted into planets, and so on and so forth. And so our goal here as part of this chapter, and of course this is a lifelong dream for many of us, is to follow the trail of water from formation to supply to young planets. What happens as planets are being born? Okay, so this, of course, is our starting point. This is why we're here. But also, this is a useful slide for some context. We are on a planet that is rich in water on the surface, rich in carbon on the surface, according to our eyes. We actually have a fairly, by mass or by volume, water-poor planet, and on the surface, a carbon-poor planet. That's another story. So, when you want to talk about supply of water to terrestrial worlds, apparently, by volume, by mass, you don't need that much to lead to what we call intelligent life. We can debate that issue. So, basics about water first, okay? So, I'll start with the observational how we observe it astronomically. Of course, in the solar system, we can actually go places and tear apart the rocks. So water is an asymmetric top molecule, so you have the two hydrogens out like this, you don't think Mickey Mouse, and it can vibrate in all kinds of ways, and I'm not going to demonstrate it all because you don't want me to do that. So here is a detection of water in the Earth's atmosphere from Galileo as it's probably heading away. And you see all these nice water vibrational bands. Now, water, of course, can rotate. Its primary rotational transitions, it depends upon energy here. So really hot stuff is coming out in the mid-infrared, and really cold stuff coming out in the far infrared. And of course, we have an atmosphere. Atmosphere impedes those photons from space from reaching the ground. So we have to spend a lot of money and go to space to try to detect this. Now, again, you can see the portfolio of emission changes as you go to different temperatures. So, the rotational transitions and the vibrational transitions bear information on the conditions under which they are emissive. And one of the things they also portray for you is the amount of water with some difficult work. All right, and this is the confusogram for many astronomers. This is the chemistry. But this plot, I'm not going to get into the particulars. This is 20, 30 years, decades of really amazing work. And so we really focus a lot on how water forms, and it's summarized in a nice review that's going to come out soon. What I thought I'd do instead was rather focus on the conditions and what happens, where does water form in abundance and where does it not form in abundance, just to give you a context. So if you're in LTE, that is, in very high pressures, the wording I had for that was the chemistry that would happen if you waited forever and a day. Well, okay. Regardless, if you're in that condition, you would take any oxygen that's not in the refractory component and stick it in water. Water would be very rich. And so that's where we spec the inner part, the inner mid-plane, and so on and so forth. If the gas temperature exceeds 400 K, you have neutral-neutral reactions that basically take the water oxygen and stick it in water. And if the gas temperature is less than that, you need a source of ionization. This is relatively inefficient for things to go. That's in the gaseous state. In the solid state, well, okay, you could freeze things out if you're below the sublimation point, and if you're below about 30 K, then surface chemistry can make a lot of water by taking the hydrogen atoms. All right, and so there's a nice movie to show you the water formation on ice surfaces, again, using all that wonderful theoretical work. This is provided by Van de Schaak and Lamberts. So there's our typical interstellar grain. You're going to see all the atoms, oxygen, and so on. This is really awesome. And I'll let it go. I was thinking of a soundtrack for this, but I didn't want to get Avina mad at me. So there's different pathways. Water may not form directly, from H plus O to OH and OH plus H to H2O. You may go through peroxide and O2 and various other things. But it's a very efficient process. Okay. So you make water ice actually very efficiently, actually at cold temperatures mostly from on the surface chemistry. And once you get it, you can destroy it in a bunch of ways. In the gas, if it's hot, UV photons are often present, and that's a big limiting factor. If it's colder than this, that's not very cold by interstellar standards, but then the ion molecule chemistry kicks in, but you need some ionization for the ion molecule chemistry to sort of reset things. On the solid state, of course, it's a pressure-dependent condensation front, but you will evaporate your ices. And if you're below that, you need some non-thermal process to remove your water from the grains. And we actually do think this is happening, and it's seen in the laboratory. In particular, Karen Oberg has shown that UV photons can desorb water ice molecules and put them into the gas. All right, so let's go through our story, water formation in space. So we're going to start in the beginning. These are prestellar cores, so no star, centrally concentrated, cold. Quite the effort to try and detect water vapor. Water ice has been known for some time that these regions are rich in water ice. We looked for water vapor many years, and Paolo Caselli was tried really hard, spent a lot of time. Big success. So we see this profile here, emission and absorption. That's something that tells you where the systemic velocity is. The key point here is that we actually see some emission. That actually, from the excitation, really tells you that this is water vapor in dense gas. If we measure the abundance, we find that the gas phase abundance is really low. The ice is high. So the water and the oxygen is in the ice in the prestellar stage, okay? And we also don't detect O2 only in one cloud, and its non-detection is actually also part of the story of putting O in water ice. So what I want to give you as sort of a takeaway message from this phase is that water is formed as ice during the prestellar stage in abundance, and that's via the surface chemistry. That's what we've learned there. Now you have a protostar that's born, okay? So there's this cold envelope on the outside here. We've heard about that. In the center, we have what we call a hot core, where it may be hot enough to perhaps evaporate ices. There's a young forming disk, small, and then an outflow, which perhaps has some shock heating to get you to very high temperatures. And based upon our chemical expectations that I described to you earlier, we expect this thing to have not much water because of freeze out. Maybe there's some ice evaporation here in the hot core, so this should, in theory, be booming in water vapor if you get above the sublimation temperature. This is what we'd love to detect, the young protodisk, and we're getting there. We've seen that already, but this is hard. And of course, the shocks we predict would be water vapor rich, and indeed, there's been a host of observations over years to show that that is the case. So here is some of the Herschel observations of shocked water vapor. And you can see these really broad lines, tens of kilometers a second, and then if you map it, you get this nice bipolar outflow. What we know, so this is work from Lars Christensen, Brunello Nacini, there's also all kinds of others, Claudia Cadello. So we know that water is abundant, certainly compared to the prestellar stage, but this water is going out into space, all right? So this is not really part of planet formation. But this is a key part of the story of water in space. All right, so the take-home message from this is water and outflows is abundant, lost to space, not part of planet formation. So now we want to transport things from cores to disk. We were talking about this in Colette's talk. So finding water emission from the so-called hot core, should be really abundant, have a lot of oxygen, and should be really emissive. Problem is you have these really broad profiles in an optically thick line, so it's very hard to trace the inner region buried in this emission from the shock gas very close to the star. All right, so this is very hard work done by Ruud Visser, and also Coutances also has some work on this. And in this case, we detected water 18, is very narrow line, 5 sigma detection. And it's very, you can detect it, you can maybe measure your water column density, but then how do you get an abundance? Because this is on very small spatial scale. So what do you normalize it to? And so we try to figure that out. It's consistent in part with the very high abundance from evaporation, and the question is this part of the planet formation story? Is this hot water then provided to the disk? We don't know. But one thing we do know is when we look at this with higher resolution, some beautiful work by Persson and Takei, where they looked with AMA and the SMA. So this is water emission at water 18 emission at 203 gigahertz. You see it's detected. If you go to even higher resolution, 690 gigahertz, they're still there, size scales of 20 AU. All right? So this is perhaps the young forming disk, we think. It's detected, and the abundance is less than 10 to the minus 4. That's sort of our fiducial abundance for the water ice. And so if it was all evaporated ice, then we should have seen it with higher abundance and more booming lines. We don't. So that suggests that water is mostly as ice in this young proto-disk. Now, of course, we saw this plot earlier from Ruud Visser's work, where he followed streamlines and asked what happens to it. So if you have material infalling, one possibility is that if it's falling fast enough, it may hit the disk, have a shock, evaporate your water. And this is a very common thing that you'll find in some of the literature discussing the solar system. And another question is, well, you may get through something where you heat the water, evaporate it. Does it stay in the gas? Maybe it refreezes. Episodic accretion, maybe this happens all the time. All right, there could also be photo-driven processes. In Ruud's work, he found that the stuff that would suffer an accretion shock actually goes into the star. So it has to fall into sort of like the inner tens of AU or 20 AU, and most of that material goes into the star early on. So that doesn't seem to be a factor in the models, and so the prediction is that most ices go into the disk unaltered. All right, so we think that water is provided this mostly as unaltered ice. The infall stream does not evaporate. Water does not then trap any volatiles for delivery. It's a big idea about how to trap noble gases. If you evaporate this water, when it refreezes, it can maybe bring some noble gases with it. All right, but, okay, and we have to be clear here, this is just, a handful of observations. We're on the cusp of a lot more, obviously, and one model, very good one, but this is the least studied or known stage. So, now let's talk about disks. All right, well, Klaus and Colette and Joan and John and a whole host of excellent researchers over the past couple years have really worked hard to study water in disks, both with Spitzer and Herschel, and this is just one plot showing a Herbig AEB star and a bunch of T-Tauri stars, and this is the farthest of water lines. The demographics are that the water to CO ratios are typically, unity, maybe a little bit below unity. If we think that CO has an abundance of 10 to the minus 4, that's our fiducial point. The emission is definitely arising from warm or hot gas, depending upon how you want to say it. It has very high column density. It's not found in the gaps in transition disks, and it's not detected in A stars or B stars. All right, so that's what we know from the hot water. So hot water vapor is very common in the inner disk, the inner few AU. All right. So demographics of cold water emission. So this was a very long integration with Herschel Hi-Fi to obtain this beautiful detection by Michael Hogerheide of both spin states of water. This is in the outer disk where the temperatures, the dust temperatures, are well below the freeze-out temperature of water vapor. So water should be present as ice. We shouldn't detect this water, but we do. And so we believe that this is this non-thermal process called photodesorption that is giving us this tenuous layer of water vapor on the surface that we detect. The demographics is, Mikhail is working on this. We did very deep integrations on 7 systems, T-Tauri, and we only have 2 detections, so it's this one and one other in an AE/BE star. And we also did shallower surveys in more systems, and we didn't detect any emission. So cold water is rare. Now, it's also possible to look for water as ice, all right? And this was known from the ISO days. This is a Spitzer, or an ISO spectrum, and you see this bump here at around 60 microns that is associated with crystalline water ice in emission. You can also look for ice in absorption if you get favorable geometry so that you can look through the star, providing maybe the inner disk, providing a background source shining through the disk that you can get your line of sight oriented, and you can see water ice as well, this time in absorption. Of course, there's a very nice paper by Melissa McClure where she uses Herschel to look for crystalline ice features and has a detection. So there'll be more on this coming. So about 20 to 50% of cosmic O is in water in this emissive layer. And more this is a hydrated silicate feature here, and more sensitive Herschel observations do not confirm this. So we have not yet seen hydrated silicates, which would have been very exciting. All right, so this is the theory about trying to explain what we're seeing. Very nice paper by Peter Wojtka. So this is water abundance here. This is height, if you will, normalized to radius versus radius. So we can see a bunch of reservoirs. There's a lot of excellent models here. So this is our midplane here. This is where it's hot enough for you to evaporate ices, also to have the high temperature chemistry. And there are things that can limit the water abundance there, but we have the expectation that water will be very abundant in the midplane. Then there's the surface layer, this surface water. This is where the temperature can get high enough. You will evaporate ices. You will also activate the hot chemistry. And also, you can get something I'll tell you about called water self-shielding here. So this layer is very important because this is the layer that we're detecting astronomically. All right, it's not clear. We do not believe we have yet detected water in the midplane. So when Colette was talking about snow lines, and she was very careful and acknowledged this, that we're seeing water on the surface. And what we don't know right now is that an evaporation condensation front on that surface, or is that a hot temperature chemistry turning on and turning off surface, and the midplane is doing something else. So it's also, if you look at the column density of water vapor that's detected, it's only 10 to the 17, and you look at the ultraviolet opacity of water to UV photons, you can find that the optical depth in water exceeds unity for ultraviolet radiation, such that water actually can shield the entire inner disk from UV photons. This is important because dust grains are settling to the midplane. All right, and so the UV normally will just track with the dust grains as they settle. But if water is forming efficiently and fast enough, it can actually stop that process. So this is a model by Tom Bethel, where if you have this dusty midplane, you don't include this effect, the stellar photons go down to the dust surface. But if the temperature is high enough, if you have H2 present, water can actually survive in what would then be a harsher environment and allow for other things to happen deep down below, including having water vapor in the midplane. So then there's this third reservoir out here of vapor, the reservoir of gaseous vapor. This part here, this is the layer that we're seeing with Herschel in the ground state transitions of water vapor, the cold water vapor. That's the photodesorbed vapor layer. And that really just depends upon what the UV is doing and what the ice-coated grains are doing. Okay, so the take-home message from this is that the surface layer is emissive. That's what we detect astronomically. Hot water is common, cold water is not. The midplane remains hidden to us right now. The ice reservoir, we detect it directly, emission and absorption, it's hard work, and also indirectly with this method of photoabsorption. You need the water ice for the UV to pop the molecules off for us to see it. All of this is very difficult to do. All right, so this is where we want to go, of course. We want to put our water in our grains, put our ice-coated planetesimals, stick them in our embryos, and then make us. And water ice is, as was noted, is very useful in promoting growth. So, having water in the solid state is very useful in making bigger things. And, we talked, Leonardo gave an excellent talk, showed us about dust traps. That particular dust trap is beyond the snow line. So it's a nice little factory for making KBO objects and things. Now this can have effect, the snow line can have effects on the composition of planets, and this is something that's becoming quite an interesting thing in the past couple years. And I'll try and work you through it. So you can imagine here you have your disk here, star, all right, and it's hot here and getting colder going out, and there can be different evaporation fronts. So we'd have, say, the water snow line, CO2 snow line, and then the CO snow line radially working your way. And the example I'm going to give you here, talking about the C to O ratio that's in the gas and the C to O ratio in the ice, is assuming that these are the only things I'm talking about, water, CO, and CO2, and there are other carriers, potential carriers of oxygen when I go through this example here. That's just a highlight. Now, if you think about this, all right, why am I doing this? Because if the C to O ratio has a variation in the gas in the disk, all right, when the giant planet forms, it's going to accrete that gas, and it's going to have a C to O ratio, perhaps commensurate with that radial distance. And the ices go into the terrestrial worlds. They're going to have something different, all right? Of course, there can be other factors that can scramble all that up, but this is the basic idea. So, if you're inside the water snow line, all right, roughly all the CO and CO2 are in the gas, water's in the gas, so the C to O ratio in the gas is on the order of 0.5, all right? If you get here inside the CO2 snow line, water has frozen out, okay? Inside the water snow line, CO and CO2 are in the gas, water's in the ice. The gas phase C to O ratio is 2 to 3, and the ice is actually going to be much below that of solar. So you form your giant planet there, you get a different C to O ratio than if you do here. And if you go out here, the C to O, CO is in the gas now, water, CO2 in the ice. This is the C to O ratio. It's carbon and oxygen in CO, and the ices have something less than solar. And then out here, it's something different again. And there's been some nice papers discussing this. So why does this matter? Well, now the exoplanet folks are going out making observations and saying that perhaps there may be evidence for some of these effects. Very nice paper here by Madhusudan. So this is a predicted spectrum of a planet relative to the star, wavelength, for different C to O ratios. And these are all the water bands you see here. You change the C to O ratio, these water bands go away. So the amount of water in this giant planet atmosphere depends perhaps on the radial location where it's born relative to these different snow lines. And also, one might have to think about planetesimal pollution, since we know that Uranus and Neptune, we believe, had some planetesimal pollution that raised their D to H ratio in HD above that of solar. So, in our solar system, we can play this game too. In fact, we damn well better. If we don't know our own giant planets, what are we going to do about others? And sadly, the oxygen abundance in Jupiter is not very well known. The Galileo probe, that was one of the key things that it was supposed to do, went down into what they believe is a dry spot in the atmosphere. So here's the measured abundance of oxygen. We think it's going to go up. And Olivier has a nice paper where he discusses what you would expect if you had a C to O ratio of 1 or a C to O ratio of 0.35 for the oxygen abundance, and what you would expect for carbon. And so if we can get this number down, we can begin to test these theories. And luckily, Juno is now shooting its way to Jupiter, but you have to wait a couple years, plus who knows how long before NASA tells you what's going on for you to find out that particular result. All right, so now we want to put water on Earths. So then you have to think of this condensation sequence, and Colette had a very nice plot of that. What we know is that, there's a refractory component that's, takes a lot to evaporate it. And the silicates are the seed of terrestrial worlds. There's also a carbonaceous component. They don't get into Earth. Mike Meyer was talking about that. Volatiles, okay? So these things, water, helium, organic, CO, so on and so forth. Of these, hydrogen and helium are the most volatile. They're clearly in the gas. Water and organics are intermediate. And then you have the very volatile substances that need very cold temperatures. All right, so in the solar system, there is an inferred gradient in the water content, and Morby was talking about this in his question, and this is a very nice figure that I borrowed from his review. We borrowed, I should say. So this is the water mass function versus distance to the sun. These are the different types of chondrites, and the N-type chondrites have been linked to E-type asteroids. So this is a plot of different asteroid types in the asteroid belt that's from reflected spectra. So here's the E-type asteroids, and ordinary chondrites are listed S-type, and carbonaceous CD out here. So there appears to be a gradient of the water content as you go outwards into the asteroid belt until you get to main belt comets, which are very rich, water-rich, and then regular comets, which are also highly hydrated. All right, and so if you take this, the idea then that the stuff at the Earth would be very, very dry, and here's the Earth's water content, and I told you mass fraction very, very low. All right, so this provides us an idea of what was going on for water in the solar system, and the snow line was somewhere out in this region here. All right, so what do we think, or how do we think you make terrestrial planets and get water to them? All right. So one idea is that the Earth formed dry. The small dust grains, the 1/10 of a micron dust grains at 1 AU would have a temperature of several hundred Kelvin, well above this evaporation temperature for water. So your primordial grains that everything's made of aren't going to have water in them. So you're not going to make icy planetesimals, and that's reflected in that plot that I just showed you. All right. In that case, you need to get planetesimal delivery. And there are sources beyond the snow line. You could argue about whether it's the outer part of the asteroid belt or comets or whatever, and the dynamicists have very good stories that they will be telling you about. And so the one question is, does this delivery happen early or late? That may matter. Another idea is that the Earth formed wet. That you're bathing the young Earth in this sea of water vapor that we're detecting. All right? Well, maybe it accreted that water vapor along with its initial atmosphere of H2. We think the Earth had 2 atmospheres. In the beginning, it had an H2-rich atmosphere captured, and that was then lost to space. And what we have left is the outgassed atmosphere. All right? The problem with this thing is that timescale is an issue. If you look at what people think about Earth formation, the hafnium-tungsten timescale for core formation is tens of millions of years. And astronomers in this room would tell you that we don't think the gas is around for tens of millions of years. So there's this timescale mismatch, perhaps. So it's generally accepted, mostly actually from isotopic evidence in the atmosphere, not by my argument about timescale, that the Earth atmosphere was generated by outgassing and by proxy water as well. And there's a nice review by Kevin Zonley that discusses this, and there's lots of others out there. Another idea is that hot grains trap water. A paper by Moralidharan and King about this, and also the late great Mike Drake was involved in this. So the idea is that, you have porous aggregates that have hills and valleys, the grains. Maybe you trap water in the valleys. And, as an astronomer, I love that. The water vapor I'm detecting matters. Yay. But, if these grains exist, we currently have no record of them in the solar system because, there's that gradient, there's that inferred gradient in the asteroid belt. So that's a possibility, but it's a question. So this is the idea of planetesimal delivery. You're going to hear a lot about this, I assume, later in the conference. And this is just one example of really, I think, fantastic models that have been done. So if you start out, this is from Sean Raymond. So this is eccentricity, semi-major axis. You start out with some distribution of planetesimals, some dry, some wet, and you stick a giant planet in there. In this case, the giant planet migrates in, it excites things, and it starts moving material around such that what forms at 1 AU should have been dry is now wet. In this case, a giant planet is moving around in the terrestrial planet forming region. You don't necessarily have to do that. Jupiter and Saturn, if they form early enough, could influence things, and it depends upon their eccentricity. So this is all wrapped up in the architecture of the solar system. So when there was a question about what might be different about the solar system, well, different solar systems have different architectures of the giant planets. In this picture, you would then get a different distribution of water contents in the rocks via this process. All right? So the habitable zone can then be seeded with water, but it has various dependencies that the experts can tell you about instead of myself. But I can tell you about this, deuterium fractionation. There'll be a nice chapter discussion about this later in the week by Cecilia Ceccarelli and presented by Paula Caselli. So deuterium is perhaps a chemical fossil. Its abundance is about 100,000 times below that of H, set by the Big Bang. And at temperatures less than 50 K, there's a vibrational energy mismatch between the HD and the H2, such that if you have a reaction with HD in something, it prefers to transfer the D as opposed to the H. And so you can enhance the ratio, the D to H ratio, in whatever the product is. So the idea is if the temperature is less than 50 K, your D to H ratio, say HDO over H2O, would then be greater than the primary reservoir. And if you started out with a high ratio and you stuck it in the gas, you would enhance it further. If you're in this regime, greater than 50 K, then everything's the same. And if you started out with the high ratio and you flood it into the gas, it would go down. If the temperature is greater than 100 K, you evaporate your ices. All right, and we do not believe that, based upon various considerations, that this will change, or photosorption will change the D to H ratio. If you reprocess it in the gas, you're in this regime, it goes down, unless you're in LTE, in which case you can get as much by a factor of 3 enhanced. And Francois Robert had several reviews where this is discussed. And there's a very interesting paper by Wang-Fei T that suggests that on the surface of the disk, where it's photochemistry driven, you may actually be able to get deuterium enrichments. And this threw a wrench in the picture of trying to understand this. And so that's a very interesting possibility that needs to be explored, and I'll show you why. So this is the money plot. There's lots of great D to H ratio plots out there, and this is Magnus Persson's nice attempt at this. This is the HDO over H2O up here. This is actually HD over H2. This is the interstellar medium and the sun. All right, there's the Earth. So we're about a factor of 10 enhanced. That's above this LTE factor of 3. So this tells you that there was some supply, we think, from cold temperatures. Perhaps. There's the moon. All right, there was a measurement that suggested it was higher than the sun, or than the Earth, than SMO, standard mean ocean water. New measurements suggested it's not, so they can argue a bit. There's CI chondrites, bang on the Earth ratio. Jupiter family comets, these are believed to originate from the Kuiper belt, about the same as SMO in the small sample that we have. Oort cloud comets, larger sample, still small. These things are believed to originate in the giant planet-forming region. So not certain, slightly higher than SMO. And then we've been able to get D to H ratio from protostars now in that hot gas that I was showing you, around tens or hundreds of, about 100 AU. And that is comparable to what we're seeing in Oort cloud comets. And this is what we measure in the actual ices. All right, so these are the potential source terms for water to the Earth. And so at face value, the things that have the same D to H signature are CI chondrites and Kuiper belt comets. Or if you did Oort cloud comets, you have to mix them with something that's lower to bring them down to SMO. So that's an interesting constraint. And so people have tried to do this. So for planetesimal delivery, again, there's plausible sources, the water D to H ratio. However, if you take any contribution from the outer disk and having some mixing coming in, if comets are reflective of the outer disk, you have to mix it down. All right, and so that is perhaps saying that there was some D to H ratio from the cold interstellar phase where the deuterium enrichments are first implanted. Perhaps I should have said that. In the prestellar phase, that's when the deuterium enrichments are implanted in the ices. So for atmospheric capture, well, there's the timescale problem. The D to H ratio at water at 1 AU should not be enhanced because of chemical considerations, but then there's this T paper. If you can mix the surface down, you could do that. Atmospheric escape, if you get in the atmosphere, it's mass dependent, so that may happen, but again, we don't think the D-to-H ratio does things. That has the timescale problem. And this hot grains trapping water, again, it's at 150 K, you should not have fractionation, significant fractionations. But if you had surface mixing from some surface reservoir, perhaps you could do something. So, where are we getting here? Well, water is clearly an important tracer. I think I've tried to show you how you might be able to use water to actually probe observationally both giant planet and terrestrial planet formation. Right now, if you look in the literature, it's pretty clear that planetesimal delivery models are favored for getting water to the Earth. If you make Earth water-rich in the beginning, then you probably have to get rid of its water. And that's an interesting problem, all right? And we think that water partially formed under cold conditions because of this cold, the deuterium signature, which is higher than you would get from chemistry at 1 AU. So, water is made in the prestellar phase under cold conditions as ice. That's pretty clear. Deuterium enrichments are implanted. We think that collapse, we're certain that it seeds the disk with water ice, and our initial suggestions are that it is mostly unaltered. That's an observational statement that will gain greater credence or not in the coming years. Water vapor is readily detected on the disk surface, less so in the outer regions of the disk where we see it as ice. The midplane remains hidden. Water is important to make planets, all right? Accretion by giant planets, and depending upon what's going on in the carbon reservoir, may change your atmospheric composition dramatically, and it may depend on birth location. Jupiter is the key test here. Water is common. That's the one other thing that you can take away from this. Water is present in our protoplanetary disk very readily, and thus perhaps the delivery to young Earths may also be common. If we want to look forward, what can we do? Well, we really need to understand this core-to-disk connection, and we have little observational constraints on that, but again, as you heard it before, AMA, and this time it's real. It's going to happen. All right, there is the movement of materials, both ice and gas. The gas could be moving in. You could have deuterium fractionated gas in the outer disk. Maybe it moves in and gets unfractionated. Maybe it moves out again. The grains are doing, random walking all over the place. So, what does that mean? Okay, and we need some observational basis for this. All right, our observations see the surface. What does that really tell us about planet formation? Okay, the deuterium fractionation is part of this. I didn't talk about oxygen isotopes. Meteorites have an odd oxygen isotope signature. We can try to use ALMA to probe that. Can we detect the midplane? HCO plus would strongly react with water. If water is present inside 1 AU, HCO plus should be present further out. It might be a way of probing the water snow line. But then you need ionization, and the best thing we have is cosmic rays, and my student Ilse Cleese will tell you that the cosmic rays don't make it in because of winds. So that's a question. Juno measurement of the deep oxygen abundance in Jupiter is critical. And of course, we need to have more understanding of this diversity and D-to-H ratio in the cometary record. Thank you very much.
Thanks, Ted. Time for some questions. Joel.
Joel Kastner, Ted.
Hi, Joel.
You get the ionization in the midplane from X-rays. They far overwhelm cosmic rays in terms of ionization rates. So I don't think there's a difficulty with that. It's a question of understanding it both observationally and through models.
You can read our paper. We put the hard X-rays in. Don't do it.
Well, okay.
Sorry. You can try it yourself, but yeah.
No, I won't try it.
Yeah, okay.
But Uma Gordy will try it for me.
She can try it for you, but we did it. Sure. We took your 10, 20 keV X-rays, some sort of parallel towel, and did the scattering, the whole thing, and you don't get enough ionization to power things.
We should talk afterwards, because we need a realistic X-ray spectrum impinging on a disk, and that experiment has not been done yet in models or really observationally either. So.
Fair.
Rude.
University of Michigan.
We don't talk, apparently. Go ahead.
No, not enough. Ted, as you know, the amount of water on Earth is highly uncertain. We don't know whether there's 1 ocean's worth or 10 or maybe even more. How does that affect the actual D/H ratio on Earth? How well do we know that the SMO value is really the relevant D/H value to compare to?
Right. So there was an expert in Boulder, Joe Smith, who told me that the deep water would trap, I think, one form over the other, and so the D/H ratio in the Earth would then not reflect the bulk D/H ratio. And that just annoyed me. So there's not much I can do about it. If the Earth, yeah, so it's possible on probe. So you could imagine if it was 100%, if there was, if we have 2 oceans, maybe our D/H ratio is 2 in one direction or the other. I don't know the answer to that, so that's a problem. And people just have to be aware of that issue. And of course, people the mantle needs to be hydrated for you to have plate tectonics. So the Earth has more than one ocean, and if you stick water in the core, you could have as much as 100 oceans. But the experts, it's not me about that. So yeah, that's an issue.
All right, let's go up to Rachel.
Hi, Rachel Smith. So regarding the oxygen isotopes, I just want to mention that in terms of getting the precise column densities that we think are necessary to compare to the oxygen isotope anomaly that you touched on in meteorites, we have these CRIRIS observations that look at that. And my understanding is that that's the instrument that's necessary to actually address the anomaly within tens of percent, and so, or less than 10%, I should say, to actually look at that mass-independent fractionation. So if ALMA is able to look at those column densities to that precision, that's kind of news to me. I didn't know. So maybe you can clarify
Sure.
what you meant.
So no, ALMA's never going to get to the precision of meteoriticis. It's always fun meetings where they go to fractions of percent, and I'm like, yeah, factor 10. Yeah, we can show that that enrichments in the oxygen isotopes, as you know, could happen on even larger scales than seen in meteorites. And if you could take that and mix it down where something's not happening, you don't need to have a huge amount of it to have a big effect on those scales, right? So that's, yeah, there is a mismatch, but there would be huge effects that we can detect astronomically that if they're present and if you can provide them in the right form at the right time, they could have a differential effect. Okay?
Let's go up to the left-hand side and then down to Colette.
Hi, Ted. Joe Mottram from Leiden Observatory. I just wanted to comment on your first bullet point up there, to say that we already have evidence of the flow of water in particular from cores to disk sort of scales from some WISH observations of low-mass protostars, and that from some detailed modeling we find that actually we need to include density-dependent freeze-out, that we need more freeze-out so it's more likely to be ice that's falling in at the smaller radii.
Oh, thank you, Joe.
Colette?
Colette Salick from NOAO. Oh, that's better. So my question is about the nice Morbidelli review plot showing the water. My question is, so I realize it's a log plot, I think, but it seems to show sort of a smooth change in the water vapor or water content of bodies in the solar system. So do you think that this is inconsistent with the idea of a distinct drop-off in water at a snow line, or do you think maybe it's evidence for kind of a smoothly evolving snow line throughout the history of the formation of the planets?
I don't know the answer to that. I mean, certainly the snow line was believed to have moved, and maybe this is where it was set in at a later stage, but can Morby comment on what he did to construct that, and whether he...
Well, he's deciding whether to answer that. Maybe Ralph can.
Yeah.
Yeah, Ted, is the D to H ratio that you've just shown in the person plot,
Yeah, go ahead.
do you see evidence of that being reflected in these in these other disk systems that you're looking at? Is there any
So
hint that these are somewhat similar, or?
Sure. So we see DCO plus in disk systems, and so we know that some fractionation is happening on the surface of the disk. The D to H ratio that we measure in protostars again, appears to be commensurate with sort of Oort cloud values. But getting into the disks, the young disks right now are, well, the T-Tauri solar nebula analog disks. We're not there yet. That will require ALMA in its glory.
Morby.
So I've been asked to comment on this plot. Well, this is an empirical plot, so we just take the water fraction in mass measured in meteorites and relate it to the location of the putative parent bodies of these meteorites grossly. So we do see a steep gradient, but it's not an on-off process, as was noted. I don't think this is trace of a snow line moving, because the chemistry dating suggests that carbonaceous chondrites and ordinary chondrites form at the same time in the disk. Jonathan Lunin and his student Cyr had a nice paper several years back in time suggesting that planetesimals, icy planetesimals formed at the snow line can be sometimes scattered inwards or go inwards by migration, and they can deliver part of their ice to other planetesimals which are forming in a dry region, so delivering a little bit of water and of course less and less as you move further inwards. There is, I think, no better explanation than that up to now.
Thank you. I think that's why Protostars and Planets is great.
Question in the very back.
Okay. Just a comment on the possibility of early delivery. This is Diego Turini from the National Institute of Astrophysics in Italy. In principle, as Morby was saying about the delivery by icy planetesimal and the transport mechanism, even if you form a giant planet that is not migrating and you keep it beyond the snow line, it is still possible for it to send icy planetesimal in the inner regions. It is an old idea of Safronov that has been studied a little during the 70s, and we are now trying to re-explore. It works reasonably well, apparently, for the asteroid belts, but that doesn't mean that the water can stay there because the bodies are small. But in principle, you can deliver icy bodies into the inner regions just by forming a giant planet, even if it is not migrating extraordinarily by large amount.
Right. Yes, I agree. Yeah, I think that's you don't need to have the migration. The migration can have a big effect, but the eccentricity matters, and there's just, again, there's a whole suite of awesome models that I'm sure you'll hear about a little later on that will summarize all those points. Thank you.
I was hoping if I kept you all here long enough through the lunch break, your questions would get more and more aggressive towards Ted. But,
yes.
But since that's not happening, I think we probably should move on to lunch. Let's thank all of our speakers this morning again.